So, all right, we're going to try to cover both those needs for everybody here, and the more you know about designing, we think the better you'll be at reviewing, so that'll help out as well. So, bioretention design, we've decided to hold the brown bag on bioretention because that does seem to be one of the more common BMPs that are used for both water quality treatment and some stream bank protection and things like that. Excuse me. But there are many other, there are about 25 other BMPs located in the technical manual under site development controls. So information on bioretention that we'll go over as well as other BMPs are located there. So a quick agenda, we're going to cover some basics of bioretention. We'll go through that pretty fast. The next part is design standards and criteria. We reviewed lots of different manuals when putting this slideshow together. Some of this stuff does come from iSWM, but there are a few things that come from various other manuals across the region. Next, Mike's going to take over on maintenance and inspection, and then we're going to talk about bioretention that has been done in the region. So basics of bioretention. Bioretention is called a couple different things. You may also hear it called biofiltration or rain gardens. Rain gardens has a nice, pretty sound for when you're trying to build one in a community. It sounds like somebody wants in their backyard, so that's a good trick to have up your sleeve. How do they treat water quality? They treat it through filtration, infiltration, and through biological means. I'll go through a couple of steps of those layers and where each treatment practice takes place. They're applicable to mostly small drainage areas. You wouldn't want to put a bioretention pond to replace, say, like a regular detention pond or a wet pond. These are for 5 acres or less, preferably 2 acres or less. So parking lot islands, small areas like that is what they're used to treat. Length to width ratio, this is just some basic when you're designing. You want to look at having a 2-to-1 length to width ratio. That's mostly so you don't short circuit your system. You're not putting all of your flow into one spot. You're letting it span out over a certain area. And then drain time of less than 48 hours. A lot of people wonder, why would you want a drain time of less than 48 hours? That goes to the next question. Common questions when it comes to bioretention design. The most frequent one we hear is this going to be a giant mosquito pit? Is this just going to breed mosquitoes and cause problems for my community? Well, in order to answer that question, we did a little research on the habitat of mosquitoes. What we find is that mosquito eggs and larvae are aquatic, so they need water to survive. An adult lays an egg, and then that egg takes 24 to 48 hours to become a larva. And that larva takes 7 to 14 days to become a pupa. So if the water dries out, the egg dies. That's where we get our 48-hour drain time. If you can get that water to drain within 24 to 48 hours, then all those eggs that were laid are going to die. So really it becomes like a mosquito death trap. So also a good thing to mention to your community when you're talking about putting in a bioretention pond. So getting to the basics, what does a bioretention pond look like? This is a typical section. There are some variations that you can do on a bioretention pond, but typically this is what we see. There's anywhere from 12 inches of ponding water up top, 2 to 3 inches of either mulch, compost, or landscape rock, 2 to 4 feet of engineered planting soil, a filter fabric sheet, 6 inches to 1 foot of gravel, and then this would be your underdrain system. I'm going to go through each one of these layers individually, talk about the benefits of each layer, their purpose, and some of the standards that go with it. So for plan view, what does an overall bioretention design look like? Well, the goal is, let's say you have a bioretention pond in a parking lot, which would be a pretty standard application. You have your parking lot sheet flow coming towards your bioretention pond, and it's got to get in there somehow. A lot of cities around here have ordinances that require curbs around all their landscape areas. That's going to prevent any water from getting into your bioretention pond. So that might need to be adjusted, either to where their curb stops, so people don't end up parking in them, but you want to prevent that as well. So you can have just segmented curbs, or no curb at all, depending on if it's applicable to that region. After the water gets through the curb stops, you have a stone diaphragm. The purpose of a stone diaphragm is going to infiltrate some of that water pretty fast, but it's also going to help to transfer the flow into sheet flow. So you have kind of some concentrated flows coming in between these curb stops.
Is that a trench that goes all the way down to the gravel?
Yes, it does.
Is there any filter fabric separating it from the gravel?
I believe there is, yeah. So, yeah, so after we pass the stone diaphragm, then there's the grass filter strip. That's going to take care of some of your sediments, some of the larger sediments, any, you know, just bags of chips or grocery bags or plant or water bottles are going to get caught in there. The next they have is an optional sand layer. Again, that's for some quick infiltration right before you get to the main bioretention area. So the main bioretention area, it's going to be landscaped. What you'll see is trees, bushes, some smaller plants, and then mulch all around it. You'll also see a couple of, we have under-draining systems here. Most of these soils in this region aren't going to drain fast enough to warrant not having any under-drain system. So we put that in to keep the filtration, to keep the infiltration going and to catch some of that water that's just not going to go in our C and D soils.
On the grass filter strip, can you just have the subgrade hard, heavy clay and just place the black sod on that? That's good enough. That's just whatever your regular soil in the region is going to be. So you have your under drain pipe here. You're going to put clean out risers along here, and we'll talk about those. Then you also have your overflow catch basin. This isn't meant to hold a 100-year storm. It is, you know, in heavy storm events, it's probably going to flood. So you're going to need something to have, something to catch that overflow. It's usually just a drop inlet with a screen on top, so you don't get any mulch that happens to float up or any of the debris in your inlet. So that's designed like a typical drop inlet, and then it's hooked up to a pipe that takes it out, attaches to your system. We have a gravel curtain drain overflow on the other side. It's pretty much the same as that stone diaphragm. Again, the purpose is to try and infiltrate some of that excess runoff quicker. All right, I'm going to go through a couple pictures we found of bioretention ponds. This is just kind of looking through the internet and different manuals, what we found. This first one you'll see, it's pretty small. We've got the mulch layer here, and there's really just a small inlet space right there. It's a cut in the curb. It goes through, there's some riprap to prevent any erosion of the mulch, and then it goes into the drainage system. How does the street flows or parking lot flows get into that thing?
Into this thing?
Yeah, isn't that the purpose of that?
By grading, I'm assuming.
Because they got curbs all the way around.
Yeah, there's curbs all around. I'm guessing that's for any excess overflow. They don't have an overflow curb.
On the lower right. Yeah.
On the lower right.
Okay, so they expect the excess flow not goes, it doesn't go in the inlet. Get into the,
yeah, or if the excess flow overpowers that bioretention area, it'd go into the inlet. So
it hit the inlet first before it gets into the rain garden.
that would depend on the grading, and I don't have a picture of that.
It's likely sized for the first flush event. Anything greater than that is going to bypass it, and I'm assuming that's a larger inlet downstream of it that captures that overflow.
So the next one we have doesn't have any curbs on it. It's just everything drains straight into the bioretention pond. This is at the beginning or towards the end of construction, but not yet finished. Obviously, they don't have the grass in here yet, but you see the mulch and all the trees. This is another one. Not a lot of storage is going to be held here. It's pretty flat with the parking lot. There's no curbs, but there's mulch and landscaping. And then you see that overflow basin right there. This is a very large bioretention pond. It has the rock forebay down there. This is where the water would be coming in. That's going to help, that rock forebay is going to help spread it out. It's also going to prevent some erosion. And then there's a very large area where the water would pond with the landscaping and mulch. Then here's some smaller kind of urban uses for bioretention ponds. Kind of like inlets along the street, you just have landscaped areas cut into sidewalks, different curb stops bringing it into the bioretention areas. And then here's a typical parking lot island bioretention pond. You see the small curb cutouts right there that go throughout the island. They have the gravel to prevent erosion and try to help do sheet flow. Obviously, they didn't have enough room to do just an entire gravel curtain. And there's your overflow inlet. And I wanted to show this because there are lots of different designs. That typical plan view that I provided is not the only way to design a bioretention pond. These are very flexible to be fitted to what your site can hold, what it can handle, what the size allows. So let's talk about efficiency. Why are you putting in a bioretention pond? What is it going to do for you? Well, bioretention ponds have probably some of the highest efficiency of all the BMPs. They have 80% of total suspended solids removal. That's going to be the stuff that, the big things like the garbage bag or the grocery bags and water bottles, but also kind of the finer particulates that you would see if you just took that runoff and put it in a cup and held it up to the light, which would be the turbidity of the water. You also get 60% to 50% of nutrient removal. That's your total phosphorus and total nitrogen. Those are the things that, when they get into our lakes and streams, cause algae to grow and bloom really bad, and it drops the oxygen level down, and it causes all kinds of problems for fish and the health of that stream or lake. Metals, 80% removal of metals. Those include cadmium, copper, lead, zinc, a bunch of stuff we don't want in our drinking water, and that can be really hard to remove later on. And then pathogens, we didn't find any data on the removal of pathogens, but those are things like coliform, streptococci, and E. coli. So how do you calculate what size bioretention pond you're going to need? The first thing you do is calculate the volume that's going to be required, and that's the water quality volume. In iSWM, there's the requirement that you treat 85% storm event, which calculates to about 1.5 inches for this region. So in order to calculate, you take your volumetric runoff coefficient, which is that RV, and that's just a standard equation, 0.05 plus 0.009 times your impervious cover of the drainage area. So if it's in a parking lot and that bioretention area is taking just your parking lot, that's 100% impervious cover. If it's taking some other landscaped areas, then that number will be lower. So then the calculation for the water quality volume is below that 1.5 right there. That's coming just from that 1.5 inches. That's what you're trying to treat. Then you take your volumetric.
Is that supposed to be the 1-year storm?
It's the 85th percentile storm. So it's somewhere between like 1 and 2.
Whatever that is.
Yeah. A is your total drainage area in acres, and then you get acre feet, your water quality volume. So then calculating the area of the bioretention pond, Darcy's law is usually the equation that's used for any kind of infiltration BMP. It's pretty common. Sorry. And what you're calculating is the surface area of the ponding area. So you take your water quality volume, multiply it by the planting soil depth, divide that by your coefficient of permeability, which is conservatively 0.5 feet per day for bioretention soil. Multiply that. H of F is your average height of water above the filter bed, typically half of the max depth. So if you have a max pond ponding depth of 6 inches, that's going to be 3 inches. And then your TF is the design filter bed drain time. Again, that's the 48 hours typically that you're trying to get that water down before mosquitoes have a chance to hatch.
What units should you plug in here? Days for TF and the rest are feet?
Yeah, days, feet, and the water quality volume is, you need to put in cubic feet. So I've got that conversion right there, acre feet to cubic feet. So the solution is in your handouts, so try not to look too far ahead, but we're going to do a quick example. And if you don't have a calculator, then at least try to put in the right numbers into the equation. Make sure you know where they go. This example says a commercial development is being planned for a 5-acre lot with an equivalent drainage area, so a 5-acre drainage area, and 80% proposed impervious cover. They plan on treating the water quality volume with a bioretention pond. Assume a filter bed depth of 3 feet. So the questions are, what is the water quality volume, and what is the required area of a bioretention pond? So take a couple minutes, at least, if you have a phone with a calculator on it, try to calculate it out. If not, just put the variables in the equations.
What's your volumetric runoff coefficient?
It's going to be that typical, the 0.5.
Just 0.5?
Yeah, that's the conservative estimate. 0.5 feet per day is the conservative estimate for typical bioretention.
So that's what you use in your WQ sub V or RV, R sub V?
Your R sub V is this volumetric runoff coefficient, and that's based on your percent of impervious cover.
Okay, so you just calculate with that.
Yeah.
Okay,
All right, I actually saw quite a few people using pens and calculators, so that's encouraging. Hopefully nobody just flipped to the back and looked at the answers. But let's go through those answers right now. Hopefully everybody got these somewhat far in their calculations. So the first step is, again, determining the water quality volume. That's the equation. The first step to determining the water quality volume was to find the volumetric runoff coefficient. That's that 0.77. The 1.5 is that standard 1.5 inches of the rainstorm, and then the 5 is the 5 acres, that's the drainage area. Divide that by 12 and you get 0.48 acre feet. You do then have to convert that acre feet into cubic feet for the area calculation. So the next step, determine the surface area of the ponding area. You've got the water quality volume, that's that 20,909, that's just converting that 0.48 acre feet into cubic feet. The 3 feet was the filter media depth that was specified in the problem.
New message from Derry.
Sorry. The 0.5 is that standard permeativity rate for bioretention soil. So, and then the 2 is the 48 hours converted into days. That's your drawdown time. So you get a area of 19,300 square feet. With the 2-to-1 ratio requirement, the area should be approximately, I get 196.5 feet by 98.25 feet. And this is actually a scaled, rough approximation of, the blue is what that bioretention pond would look like compared to, a 5-acre development with 80% imperviousness.
Can I ask a quick
Yeah.
question, Leslie? The depth maxing out at 12 inches, where has that come from? Because obviously looking at that equation, you can maximize that depth or make that depth larger. You can certainly cut down on the size of your bioretention area.
Right, your depth has 2 factors that are going into deciding how high to make your max ponding depth. The first one is how fast you're going to be able to draw it down. There's that 48-hour drawdown time. So depending on the infiltration rate of your soil, which again, that 0.5 is a standard for design, but it is conservative. A lot of soils can give you higher than 0.5 infiltration. And then also your plants.
This assumes you discharge this thing on native soil then?
No, it's engineered soil. I'll go through the
Okay.
requirements of the engineered soil. But then the second factor is your plants. Are they going to be able to survive, greater than 6 inches or greater than 12 inches of inundation?
Now, is this measured above the gravel layer or above the surface?
That's above the mulch layer. That ponding area is what you're actually going to allow that water depth to get to. So, and then real briefly on the basics of bioretention, I wanted to cover a little bit of costs. The EPA does have a cost estimate on their website. It's pretty rough, and I haven't tested it in real life conditions, but it says that a bioretention pond will cost 7.3 times the volume in cubic feet to the 0.99 power. For our example problem, that gives a cost of about $138,000. Again, that's for a 5-acre, a bioretention pond can be 5 acres. That's on the maximum end of that size scale that you would allow a bioretention pond to treat. And this doesn't take into account other cost savings that you might incur from, the cost of a curb or the cost of additional inlets and pipes and kind of the standard infrastructure that would go in place of a bioretention pond.
What's the replacement cycle for the gravel and the planting material?
For the gravel, Mike's actually going to cover a little bit of that in the maintenance and inspection.
Because that ought to be entered in too. 'Cause
Right,
that's going to be
the lifetime cost. And I'm not sure, I don't assume EPA factored that in.